Okay, so welcome everybody, and welcome everyone who's online, listening online. So we're gonna, and I guess I have to stay close to the owl, because Alex was saying if I wander over here, then it doesn't pick up my voice. So I have to stay I'll just have to kind of stay close to it so everybody hears me. But it would help if you could see the lecture. That would be good. Okay. And let's go. We covered all this stuff, so we're going to go through. Yeah, we got about like right here, right? Something like that. Is that right? Because we haven't gotten to this slide yet, right?
No.
Right. Okay. So let's start. All right. So yeah, last we talked. We're talking about the difference between continental margins. We had passive and active continental margins. So do y'all remember that stuff? Okay. And remember. So what's an active margin? Anybody remember what active margin is?
Subduction zones.
Yeah, they have subduction zones, they have volcanoes, they have, Alex, what were you saying? Subduction zone, okay. So yeah, they have active plate tectonics going on in those margins, right? Passive margins, not so much. They don't have anything exciting going on. Well, I mean, I guess it's kind of exciting, but it's not like exciting to geologists, I guess I should say. But we will talk more about passive margins. Let me get, people came in here, okay? So anyway, where are some active margins? Where are some passive margins in the world? Now, if you look along the East Coast, all of our East Coast, are there any volcanoes on our East Coast? All right, no volcanoes there, right? So that's a passive margin. What about our West Coast? And like, are there any volcanoes along the West Coast? Yeah, there are, right? Mount St. Helen, for instance, right? That's an active margin, right? And that's because there's active subduction going on the West Coast. That's why there's a lot of earthquakes. You ever hear there's a lot of earthquakes in California? Yeah, it's true. I can attest personally. There's a lot of earthquakes there. But yeah, it's because that's an active margin. Okay. Now, if you look at this, can you all see the kind of the pink and the blue there? Yeah, it's a little bit faded, but you can see it. So the pink is showing active margins. You can see that the whole Pacific Ocean is surrounded by an active margin. Okay. So what's happening there? It's all subduction. So that's why I say the Pacific Ocean is going bye-bye. You know, it's going bye-bye because pretty soon it's not. Well, I shouldn't say pretty soon, but in 50 million years, it might be significantly smaller. Okay, so there's subduction going on, and that's do y'all know that term that we give for the big ring that surrounds? Yeah, that's the ring of fire, right? So we call that the ring of fire, and that's because there's active volcanoes all around the Pacific Ocean like that. Okay, that's because there's subduction going on, and so it's active. Okay, that's a lot of active margins. You can see that our east coast here, also the east coast of South America, that's all passive, right? Most of the west coast of Europe and Africa, that's all passive. Okay? So the Atlantic is surrounded by passive margins for the most part, whereas the Pacific is kind of surrounded by active margins. So it's a big difference there. Now, let's talk a little bit about these kinds of margins, okay, continental margins. So we call these continental margins, whether they're passive or active, we call them continental shelves, right? So continental shelves are the part of the continents that are just happen to be underwater, right? So if you dig down, if you go off the coast of say Texas, you start digging down, right? What are you going to find? You're just going to find continental crust. Okay? Does that make sense? Like you're just right off the coast of Texas, you're going to find. So if you go and dip your toes into you're on the island, let's say, and you go into the water, wade out a little bit. That doesn't mean that you've got ocean crust beneath your feet, right? It's just the continental crust that happens to be underwater. Okay? So you got to go off the coast for a little bit before you get into the really deep water. So this is a picture, this is kind of a topographic picture of, I can say, of the LA Basins. This is actually Los Angeles right here. This is Palos Verdes here, Malibu is over here. So anyway, I guess you probably wouldn't even familiar with those. I'm just being nostalgic about Los Angeles, so sorry. But anyway, this is Los Angeles. So if you notice, this part that's really shallow, do you all see that, like stuff that's colored, kind of orange, right? So that's the continental shelf, right? So continental margins, continental shelf, okay? So these are really important areas. They're very important for a few reasons that are for human society, I mean, because it actually has a lot of oil there. Okay, so a lot of oil and natural gas can be formed. Those reservoirs can be found offshore. So you've probably seen these. We got plenty of these around Texas, right? So offshore oil rigs, things like that. They have a lot of those in California as well. So they have offshore oil rigs. This amazing picture. Do you see all those little yellow dots that are off the coast of Texas and Louisiana and Florida and blah, 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 blah? Those are all offshore oil rigs. And all the little, can you see all the little orange lines connecting them? Those are all pipelines connecting all of them, underwater pipelines and things like that. So there's lots and lots of network of all these oil rigs that are keeping the oil and the gas flowing out of the Gulf. Okay, lots of oil and gas in the Gulf. We'll talk actually a little bit of detail later why that is, why there has to be oil and gas in the Gulf. Also, it's a very important fishing area. So the continental shelves have a lot of, they're very rich in terms of marine life and fish, so they're important for that as well. Okay. So anyway, I wanted to show you this. This is kind of interesting. This is the continental shelf off the coast of Texas. So you see in your lecture assignment, I talk about like the pock marks. That's number 18. Y'all see that? Now, do you see what I'm talking about right here? Do you see all these pock marks? It's kind of weird, right? Like, why are there all these like little dimples in the underwater, like off the coast of the Gulf of, in the Gulf of Mexico? So you can see all these little dimples here. There are lots of them. So what these are is actually what you have underneath the Gulf of Mexico, underneath all the sediments. There's actually these layers of salt. There's all these layers of salt. And those layers of salt formed very early in the formation of the Gulf of Mexico. These were actually forming way back in the Triassic in the dinosaur times. And that's when the Gulf of Mexico was just forming. And what would happen is from time to time it would evaporate and it would leave all of these layers of salt. You can almost imagine that the Gulf of Mexico at that time was like the Dead Sea. You all know the Dead Sea in like the Holy Lands in Israel, right? It was super saline. It would leave these layers of salt. So what's happened over time is the salt is actually pretty mobile. And as the sediments press down upon it, it forms these, it kind of like pushes up the salt. The pressure pushes these salt things up. We call these salt domes. And what happens is once they get too close to the surface, the circulation of ocean water starts to dissolve them. And it'll actually dissolve them away and it'll kind of collapse. And it'll create these dimples. Okay? So that's why you see all these dimples or pock marks in the continental shelves off the coast of the Gulf of Mexico. And I'm going to tell you why I'm talking about this, because you might be like, it seems like kind of a random feature to be talking about. This is the reason. The oil and gas industry loves these things, because these create perfect traps for oil and gas. So actually, when the oil and gas companies are going out looking for reservoirs of oil and gas, they're looking for these pock marks, because it often is from these salt domes, creating traps for the oil and gas reservoirs. Okay, so does that make some sense? So it's just a local feature I want you to be aware of. So. Okay, so anyway, let's get back to these passive margins, continental margins. Okay, so we have the continental shelf. All right, that's the relatively shallow part of the continent that's underwater. Now, that only goes down, maybe it goes down, the maximum is maybe 500 meters. That's That's it, right? It's as deep as it gets. Now there's going to be something here called a break. So do you all see the shelf break here? I kind of tried to draw it in there in white, you see. That's the part where it's the break of the shelf. So after that, the shelf break is kind of like the end of the continental crust. So then it breaks, and you notice that after that it slopes down into the deep ocean. Okay? So that's called the continental break. And what's actually kind of interesting is continental breaks happen almost everywhere at about 140 meters depth in the oceans. So you'll find the continental break. And after you hit the continental break, you're going to go into something called the slope. Okay? So do you all see this is the part where now it starts to slope down. And then the gradient becomes very steep. So that's the steepness of the slope. Okay? So it can become very steep. It can go all the way from 5 to 25 degrees. Okay? That means that, you know what I mean by like a 5-degree slope or a 25-degree slope or something like that? It's just the angle, right? The angle of the slope going down. So it's like a 5-degree up to 25-degree slope. So it starts sloping down pretty fast, okay? So does that all make sense? And by the way, you might notice that this looks like really steep, right? That looks almost like a sheer cliff, but it's because it's vertically exaggerated so that you can see it. So it's not really that steep. It's only about 25 degrees steep. Okay, so that's a shelf break. That's the continental slope. And now we're kind of, by the way, getting on to like question number 1. Okay, do y'all see that on lecture assignment 9? Okay, because we answered everything on lecture assignment 8 now, right? Oh, 17? Oh, we talked, I mentioned that right at the very end of the lecture last time. Yeah, so when you go, okay, so let me ask you all here. Let's say you're standing right here. Okay, you've walked all the way, or yeah, I guess you can't walk, but let's say you've gone all the way over here offshore, and now you're miles offshore. Okay, and you start digging down right here. Are you going to be on, at continental crust, over continental crust, or ocean crust? Yeah, so here you're still continental crust. So the continental shelf is the part of the continental crust that happens to be underwater. Okay, but this is still continent. So it's just as much continent as this is, right? These are both just continent. It's just that this happens to be underwater because of where the current water levels are, okay? If the water level rose, it might rise, it could rise. It's been rising in certain places. Maybe LA Basin might get flooded one day, and then that would be part of the continental shelf, but it would still be continental crust, okay? So I just want to make that clear to everyone that just because you're in the water doesn't mean that there's ocean crust beneath your feet. Does that make sense? It's actually like about 30% of the ocean is continental crust. It's continental shelf. Okay, so we're all together on that. You got all the questions to number 8 answered, I hope. So number 1, for lecture assignment number 9, number 1, you want to draw basically what you see right here, okay? So here's the continental shelf in orange. The break is this edge right here, where the shelf suddenly breaks and starts sloping down really fast. And that slope is called the continental slope, okay? So you got the shelf, the break right here. Right here would be the break. And then all this stuff would be sloped. And no Valerie today, right? And I see Julia Garza, right? Garza, and then, but no Julia Garcia, okay? No Tim, that's a little odd. Okay, now when you get down here to the blue, kind of you can see right at the very bottom here, can everybody see that? That blue is now you're in the abyssal plain. You're in the abyssal plain, so that's where it's really deep water. That's where it gets 4,000 meters deep. Okay, that gets very deep. So think about this, right? Right here, the shelf break. How deep is the water on average at the shelf break? That's right there, yeah, 100, so Eliana is saying it's 140 meters. So you're going from 140 meters, and how deep are the abyssal plains? 4,000 meters, right? Yeah, so you all see like how big of a dip, you're going down real fast, right? Y'all see that? So you're going down really not that far off the coast, you're going down very fast, all the way down to 4,000 meters. All right, now this part, you'll notice that I also asked for number 1 about the continental rise or the shelf rise. Do you all see that? So let me show you a little bit because you can't really see it on here too well, but let me kind of explain it. So I'm going to go right here and kind of draw like a side view of what you would see at the continental shelf, okay? So actually, let me get green because that's good for the continents, right? So here's the continent. This is the part of the continent that is above water, okay? And then I'll draw the water level in here. Okay, so there's the water level. Now here's the part of the continent that is underwater, right? So that's the continental shelf, okay? So I'm going to put that CS for continental shelf, okay? Then we're going to have, actually write it out because there's a bunch of slopes too. So that's, okay, then right here we're going to have the continental break. Okay? And then at the continental break, then it's going to start going down right away, right? So that's the slope. Now at the base of the slope, there's kind of it still slopes down, but at a smaller rate. So I'm going to make it kind of like that. And then you get the really deep ocean, okay? So this is the abyssal plain. Maybe I should get black for the abyssal plains because they're made of basalt, right? And this is totally dead. It's a loser. Here we go. Okay, so there's the abyssal plain, right? And that's the deep ocean. Now notice that right here, at the base of the slope, there's kind of like a slightly less steep hill. That's the rise. And what the rise is, I'm going to put a bunch of little dots right here. Anybody want to guess? I'm putting all those dots right there. Anybody want to guess what this rise actually is?
Sediment.
It's sediment. It's all, very good guess. That's the reason I put all those dots there is because that's all the sediment that's been washed off the continents, right? So it makes like a big pile of sediment at the base of the continents. And so that's why when you're in the abyssal plains, you'd be traveling along the abyssal plain, and it's very, very flat. You'll see how flat the abyssal plains. The abyssal plains are like, they're like the Great Plains, right? You know, you go out, or it's like Texas. You go out, it's perfectly flat everywhere. So abyssal plains are very flat. Then you would start to rise up, right? That's the abyssal, that's the continental rise. Then you'd start to go up on the slope very fast, and then you'd hit the shelf. Okay. All right, so that's what you should draw, basically. Hurry, I did it for you, so for better or for worse, I did it for you. There it is. Okay. Now, another thing I want to point out for you. Can anybody look up here and see what they think might be a submarine canyon? It's kind of obvious, I guess, in a way. But can you all see this, right? So you'll notice that there are certain places in the shelf where there's these like gigantic canyons. I mean, they're like they're so big, they're like the Grand Canyon, really. And they're about as deep as the Grand Canyon. And this happens all over the world, actually. It's not just here off the coast of LA. It's everywhere. So you get these submarine canyons. These are very, very important features, okay? So the submarine canyons are places where rivers, so actually right here is the Santa Ana River that's coming into the mouth of LA and LA Harbor, and it's going down, it's carving out, that river is actually carving out the submarine canyon, okay? So it's carving out that submarine canyon. And so anywhere where you get these rivers coming, they form these submarine canyons, okay? Very important features. We'll see those. Actually, it's kind of crazy, but like the biggest waves in the world, like where surfers go to ride the biggest waves, which are off the coast of Portugal, it's actually caused, the reason they get such big waves there, it's actually caused by the presence of a submarine canyon off the coast of Portugal. So that's why they're kind of important features. Okay. So everybody got number one, right? Everyone's good with that? So this is just kind of reviewing already what I already said, but there you go. You got continental rises are at the very base of the slopes, and they're made of all that sediment, just like Eliana mentioned. Okay. There's the submarine canyons. Now this one is off the coast of Monterey, California, and you can see like what crazy dramatic features these are. I mean, look at that. Look how deep the walls of that canyon are. Right? There's nothing like this on the continents except for maybe like the Grand Canyon. I mean, it's really, every submarine canyon is like the Grand Canyon. It has that kind of relief, like just plummeting down, a mile, right? They're pretty dramatic features, okay? So these are carved out by things called turbidity currents. Does that word sound familiar to anybody, turbidity? So like some of you came up and we measured turbidity, right? Who did that with me? Yeah, so a few of you, we measured turbidity of some water samples, right? So turbidity is just the amount of sediment that's in the water. So turbidity currents are these really like thick sediment-laden waters that are coming out of the rivers, okay? So this particular river is carrying a lot of sediment and sand and silt and clay and stuff, and it's carving out these canyons. They're very erosive. So the sediment-laden waters of these rivers are very erosive. So they've carved out these canyons. So there's a little video that is, just kind of shows you how these submarine canyons form. Okay, so it's like a little sand model video that they set up. It's put out by AGU, it's American Geophysical Union. So I'll show this to you. You hear that? Whoops, sorry. Thought maybe I turned it up and then I accidentally stopped it. There we go, sorry.
Do you like that video? I always found it very relaxing. It's like the soft guitar music and the sand. I liked it. Anyway, so those are submarine canyons. That's how they form, by turbidity currents. This is kind of a, oh, actually this is from a ROV. Remember one of those remotely operated submersible vessels, right? And they were actually off the coast. I think this is in Monterey, California. It's just kind of northern central California. And they were in the submarine canyon that I had just shown you pictures of, that submarine canyon right off the coast of Monterey, California. And they were actually down here doing work in the canyon when a turbidity current actually came in, like a big one. And some of these things are like submarine landslides. You can almost think of them as landslides if they're happening underwater. So they call them submarine slides, right? Wouldn't be right to call it a landslide. So a submarine slide. But so it's this big movement of sediment that comes roaring down these canyons. And so the ROV actually got caught in the middle of one of these things. So you can kind of see what it's like. But so they were like, this ROV literally got swept away by a turbidity current. Okay, I'll kind of do this stuff. There's the ROV, but I want to actually show you the video. So there it is under normal. Sorry, there's no audio for this video, but that's it under normal conditions, what they're doing. But then you can see it's like totally gets blacked out after a while. And you can see all this, yeah, you can see all the sediment rushing by and stuff like that. So these are the currents, these submarine slides that occur, create these turbidity currents, and that's what's actually carving out, you know, inch by inch, carving out these submarine canyons. And of course, they take millions of years to fully develop, but that's literally what happens. So that turbidity, that's very, by the way, that's very what we would call turbid water. So the water's turbid. It means that it's dirty. It's full of silt and clays and things like that. Okay. All right. So that's the shelf, right? Oh, by the way, now this is off the coast of New York. So this is the Hudson River. There's Long Island, right? There's Hudson River. Okay, that's the slope. That's the rise. And then you can see the submarine canyon, right? So you can see the submarine canyon formed by the Hudson River. And then down here, right where it gets black, that would be the abyssal plain. Okay, so you can see everything really clearly there. So it makes sense. There you go, submarine canyons, seamounts, things. Okay. Oh. Guess they changed that this semester to replace that. They made their video private, whatever. Okay. So let's go now to some more about active margins. So, you know, active margins happen where there's active subduction, right? So what are some things that you get in subduction zones that you might remember? Yeah, volcanoes. Trenches, right? So you get trenches. So now, active margins are going to look they're going to look totally different than this, because not only are you going to go to an abyssal plain, but you're also going to go and you're going to have a deep trench, right, off the coast. So these trenches form, like I said, they're off the coast in the abyssal plains in active areas, okay? And the trenches are the deepest parts of the ocean. So they're found at active continental margins. They contain the Mariana Trench, you might know, which is off the coast of Guam, the Philippines. That contains the deepest part of the ocean, which is Challenger Deep, right? So there you go. There's Guam right there, Challenger Deep, the Mariana Trench. The Mariana Trench extends all the way to Japan. Sorry, I said Philippines. I meant Japan. What's that?
Off the coast of what?
Guam.
Oh, Guam.
Yeah, sorry. If you put Japan, it's maybe okay. But there, can you see Challenger Deep right there in Guam, right? And Mariana Trench extends from Japan to
down here to Guam?
So 3 and 4 are Mariana Trench.
Let's see. Where's the deepest place in the ocean is Challenger Deep.
Challenger Deep.
Yeah. Which is in the Mariana Trench off the coast of Guam. And why are these trenches so deep? It's literally because that's where the ocean crust is subducting, right? It's sinking into the mantle. So that's why they're so deep. You know, James Cameron, he directed Titanic. Can't remember what year, but he directed Titanic. And what else did he direct? Oh, he did Avatar. So what else did he do? People laugh when I say Avatar. But, I don't know. But anyway, you know, he actually made another movie where he got in a submersible and he went to Challenger Deep. And he went all the way down. And I don't show the actual movie because it's really boring. Because there's nothing, it's funny, he gets to Challenger Deep and there's nothing there. There's just mud. I mean, there's nothing in, there's no, you think there'd be like some cool animals, right, or something, but weird animals, but there's nothing there. Because it's too deep, the pressure's too high to actually sustain any kind of animal life. I mean, there's probably microbial life down there of some kind, but but the trailer for the movie is pretty exciting. So I have the trailer here, so you can watch the trailer. But it gives you a good idea about how deep these trenches actually are. I can't do that. So there's James Cameron. Hear it okay? Okay. Yeah. It's 7 miles, it's a long way down, and there's nothing really down there of interest. So isn't that crazy? 660 feet, which is nothing. 90% of ocean life lives above that. So he's not even 10% of the way there. Now 8,200 feet. There's the Titanic, 12,000 feet. That's about 12,000 feet is about 4 kilometers. So that's like the bottom, average bottom of the ocean. But look, he's not even, okay, now he's gotten pretty good. 25,000 feet is the deepest animal we've found. Snailfish. Mount Everest can fit into the trench. And then you get 36,000 feet. And you know what they did find there last year? They sent another submersible down there. You know what they found in Challenger Deep? A plastic bag. Isn't that depressing? Yeah, but you go down there and all you find is plastic bags and mud, and it's like you could have found that in Oso Bay. But anyway, the trailer's good though. Okay. So we get volcanic islands forming here, right? And that's because that's where the ocean crust is sinking into the mantle. And then you might remember that it releases all of its water in the mantle. That lowers the melting temperature of the mantle, and that causes volcanism. Okay, so that's why we get volcanoes here, and we get these lovely little island arcs. Okay, so there's a lot of these island arcs. These are like volcanic islands. You probably know kind of about volcanic islands that form the ocean, right? So Hawaii is not one of these, by the way, but Hawaii is actually over a hot spot in the mantle. But a lot of things are like this. Japan is a volcanic island.
right? Guam, the Philippines, Sumatra, Indonesia, a lot of the islands of Indonesia, they're all volcanic island arcs. A lot of the, like Puerto Rico and a lot of like the Caribbean islands are all volcanic arc islands like this. So why do volcanic islands form around subduction zones? There's a lot of magmatism, and that's because ocean water is getting into the mantle, and that's lowering the mantle melting temperature. Lowers the mantle melting temperature. Key phrase there. Okay, I talked about that in plate tectonics, so hopefully that's not new information. Okay, so number 7, what are those volcanic islands called? They're called volcanic island arcs, okay, or arc islands or something like that. But you gotta have to get that word arcs, because I'll use that word sometimes in the test or in the lectures, and you got to know what I'm talking about. So they're called volcanic arc islands or something like that. And the reason that they're called arcs is if you actually look at them. Sorry, I went back now a lot. The reason they're called arcs is, where is this? I thought I had a map. Okay, yeah, I don't really have a good map here. Oh, here we go. Well, you can see how the Mariana Trench is very arc-like, right? You can see Japan is shaped like an arc, right? So a lot of these things, like Puerto Rico, a lot of the Puerto Rican trench is kind of shaped like an arc. So a lot of these things kind of have the shape of an arc. So that's why they call them arc islands, volcanic arc islands. Okay. All right. So why do they form a? So number 7 says, what are those chains of volcanic islands called? They're called arc islands. Now, what are some characteristics of an active margin? I mean, we'd already been talking about this several times. So hopefully you should be able to fill that out by now, right? So number 8, 3 characteristics of an active margin. So what are some things that you could put there? Trenches, yeah. Yeah, you could put earthquakes and volcanoes and things like that. You could put arcs, volcanic arc islands you could put there. You could just say subduction, right? Happens there too. Now here are some things that are characteristic of active margins. These are some things. So for number 9, here are some 2 things that are characteristic of passive margins. Passive margins have well-developed continental shelves, and they have a continental rise. The continental rises in active margins often get kind of scraped off because of the subduction that goes on there. Okay, so everybody got that? Okay, so it's on to, now we're moving away from continental shelves, and we're going to go into the next big feature, and those are ocean ridges. Okay, so mid-ocean ridges. So these are actually, mid-ocean ridges are kind of crazy, because they're actually like the biggest single features on Earth. So these would be, if you could see these from space, of course they're underwater, but if you could see them from space, it appear to be these giant mountain chains that are 10,000 miles long. I mean, they're very, very long. Right, up to like I said, 10,000 miles, and most of them are 2 to 3 kilometers high. So 2 to 3 kilometers, 3 kilometers is about 10,000 feet. Okay, so these would be really high mountain chains that are extending like almost from pole to pole. I mean, you can look at the Mid-Atlantic Ridge. The Mid-Atlantic Ridge almost goes pole to pole, right? It's not quite, but getting pretty close. So there's the Mid-Atlantic Ridge that goes through, of course, the Atlantic. The main ocean ridge of the Pacific is called the East Pacific Rise, or EPR. So you kind of have to know those abbreviations because sometimes I'll just say MOR, which means Mid-Ocean Ridge. Okay, sometimes I'll just say MAR, which is Mid-Atlantic Ridge, or EPR, which is East Pacific Rise. And you can see there's the Mid-Indian Ridge, and then there's the East Pacific Rise. And and the southwest Indian Ridge, and the southeast Indian Ridge. So there's actually something there, right there. It's called a triple junction, and it's where these three ridges are coming into an intersection. So you can actually see the Indian Ocean is kind of a little weird because it's got these three different rises, three different spreading ridges. Okay. Okay. So how long are some of those features in the ocean floor? So that's number 11. So did you all get that? So it's not just how tall, but how long also.
16,000.
Yeah, so like 16,000 up to 16,000 kilometers, which is 10,000 miles. So remember, in these places, this is where the buoyant asthenosphere is upwelling. It's coming up to the surface, and it's creating a lot of magmatism. You might remember that 80% of the magmatism, 80% of the volcanoes that are occurring on Earth's surface are actually happening right here. So the vast majority of volcanic activity that happens on Earth, we don't see it. It's happening underwater. It's happening, 2 kilometers underwater. So we don't even really see it. But you might remember I showed you that video of the underwater volcanoes. Y'all remember that? So it gives you an idea. So I think this is the same one. So I showed this before, right? So I'll remember that. It's this guy. This is right. I showed this, right? This guy. They're looking at the volcanism underwater. So it is. It's just important because that's, like I said, 80% of the volcanoes happening on Earth are happening this way at the mid-ocean ridges. So it's a very volcanically active area. Okay, very volcanically active. All right. So these are very important areas on Earth because, for one thing, this is where the new seafloor is being developed, right? So new seafloor, this is where it's born at the mid-ocean ridges. They're also very important for life on Earth. And a lot of people think this is actually maybe where life on Earth first got its footing, the origins of life on Earth at these mid-ocean ridges. So there's a lot of very primitive forms of bacterial life that lived here. And that's why a lot of scientists, I should say, think that. So at the mid-ocean ridges, you get these things called black smokers. And these are basically their hydrothermal vents. You can almost think of them as hot springs that are underwater. And what happens is that when the water is flowing, through the rock, okay? Because remember, rocks, they're kind of like sponges. They soak up a lot of water, and water can actually flow through them. When that water flows through the magmatic rocks, it gets very hot. And here's a question for you. Does hot water or cold water, which dissolves stuff more easily? Hot water or cold water? Hot water, right? So that's why when you're cleaning the dishes or something, you want hot water, right? You don't want to be washing the dishes with ice water. It's not very effective, right? So you can imagine this water is really hot. It's way hotter than the water you're used to, right? The water is actually, when it comes out of the vent, is 350 degrees Celsius. Does that surprise anybody? Does that seem to anybody like that shouldn't be right? 350 degrees Celsius for water? Does anybody see a problem with that? Yeah, doesn't it evaporate? Wouldn't it boil off and evaporate? Does that make sense? What's the boiling point of water in Celsius? Anybody remember that one? In Celsius and centigrade? Boiling point?
100?
It's 100, yeah. Okay, so this is way higher than the boiling point of water. So what's going on there? Why can the water be 350 degrees?
Because it's underwater?
Because it's underwater, and what happens when you go deep underwater?
Pressure.
The pressure. So the pressure of the seawater, having 2 kilometers of seawater on top of you, it creates enough pressure that you can get the water a lot hotter than you could at the surface. So this water is 350 degrees, and it doesn't boil. And it doesn't boil because of the pressure. So you can get water a lot hotter down there.
than you can at the surface. Because we had 350 degree Celsius water. 350 degrees is very hot. That's hotter than a pizza oven. Okay, it would boil off right away, right? It's kind of crazy when you think about it. It's almost like red hot water, but it doesn't boil. So this stuff is really hot. It dissolves a lot of material, and all that material that is dissolved out precipitates when it's emitted at these hydrothermal vents, and it creates these things that look like smoke. So I'm going to show you a video of this, and those are called black smokers. So have you all seen this before? Have you seen like videos of black smokers before on the seafloor? You can take a look. These are very, very common. Actually, see, you hear what he's saying? He said we have to be careful because we can actually melt parts of the submersible. So that's the black smoker. There you go. You can see there's actually a lot of life at these vents. And it's all especially adapted for life on these vents. It's very unique ecosystems. Can you see the little, right? There's a lot of unique tube worms that live here. There's the beauty shot. Maybe getting a little excited. But anyway, I think you get the idea, right? All right. So those are very unique ecosystems, very important for the history of life on Earth. I got to keep moving on, but we'll learn a lot more about black smokers because there's a lot to them. So what is that smoke made up of? It's actually, the blackness is actually made up of, there's a lot of sulfur that's coming out of these, and the sulfur and the iron react, and so a lot of that is either iron hydroxide, so that FeOOH is iron hydroxide, and there's also a lot of iron sulfide that comes out. So a lot of these are iron salts. They're iron compounds. And that's because these rocks contain a lot of iron, and it gets leached out by the hot water. And then as it gets leached out, it reacts in the cold ocean water. Okay. The sulfur here, I just want to point this out. Notice what's being emitted here. There's CH4. Does anybody know what CH4 is? Does anybody have a gas stove at home? They turn on the gas stove and they start making top ramen or whatever. Okay. That's methane, right? So it's natural gas. So there's a lot of natural gas being emitted. There's also a lot of hydrogen sulfide too. So there's a lot of sulfur and a lot of methane. And the reason I'm pointing this out to you all right now is because we're going to see that there's actually forms of life that can exist, and they instead of doing photosynthesis, they do chemosynthesis, and they actually use the chemicals present here to live. And they don't eat anything else. They don't need anything else. Just like a plant can live off the sunlight and the carbon dioxide and water, these do a similar kind of reaction. They make sugars out of the carbon dioxide, the methane, and the hydrogen sulfide that gets emitted here. So they're doing something like photosynthesis, but it's chemosynthesis, it's chemical synthesis. So it creates the base of the food chains here. And we think this is kind of where life on Earth maybe started. It didn't start off with photosynthesis like that. Okay, so it's just a lot of interesting things there. So you got number 12, you got number 13, And hopefully you can kind of explain now a little bit of number 14, right? So number 14 is that you got the ocean water circulating through these hot rocks at the volcanic vents. It absorbs and leaches out a lot of iron. And when that iron is emitted, along with a lot of the volcanic gases are emitted at these hydrothermal vents, it reacts and forms all of these precipitates of iron compounds. Okay? Did you get all that for number 14? Okay. Just say the ocean water kind of circulates through the hot rock, leaches out iron, and the iron is precipitated. You know that word precipitated? Precipitated is when like it forms solids, right? That's technically what precipitate means. It means it forms solids. It precipitates out iron compounds. Iron salts, you could put. Okay, did you all get that? Are you good on number 14? Oh, and by the way, there are white smokers too. There's black smokers and white smokers. White smokers have, instead of emitting a lot of iron, they emit silicon, barium, and calcium. They're a little bit cooler, they're less acidic, and they're a little bit further away from the ridge. Okay, so black smokers you find like right on the ridge. White smokers are a little bit further out. Yeah, if you Google, where do you find white smokers, you get some really interesting answers. So, different cities in America. But anyway, I made that mistake when I was first making these lectures. But there's some really crazy, these white smokers are really crazy. They get huge. Look at this. This is called the Lost City. It's underwater. It's not a real city, of course, but it's like underwater. And some of these things are as big as skyscrapers. Like some of these white smokers are as big as skyscrapers. You can't really get a sense of how big that is when you're looking at it, because there's no like scale bar, but some of them are huge. So another thing I wanted to show you are fracture zones. So this is number what? Okay, yeah, 15. So. Okay, one thing I wanted to point out is that not all spreading ridges are equal. Some of them spread faster, some of them spread more slowly. So if you have a part of the ridge that's spreading faster next to a part of the ridge that's spreading more slowly, you'll see how you're going to have something like this occur, right? Where there's going to be this horizontal side-to-side motion of the plates. Y'all see that? It's going to go like that, right? Because one is spreading more quickly, one is spreading more slowly. And so those are called, just FYI, those things are called fracture zones, and they have little transform boundaries. So what you see is that actually a lot of these mid-ocean ridges, these divergent boundaries, are connected by a series of transform boundaries. So side-to-side movement on those. Okay, and those are fracture zones. They usually occur at right angles to the ridge. So they're connecting different portions of the ridge. So the ridges will actually kind of look like, you'll have like a spreading ridge like that, and then you'll have a transform boundary that connects another part of the spreading ridge. Okay, so the fracture zone would be right there, if that makes sense. Do y'all see what I'm talking about? Okay. So this is a spreading ridge, this is a spreading ridge, but because they're going at unequal speeds, this fracture zone develops between them. Okay. I don't really have too much to say about them, but I just kind of want you to be aware that they exist. And know what I'm talking about if you end up running into one of them.
All right, so the next part of these abyssal plains. So abyssal plains are the very deep part of the ocean. So it's like the deep ocean. Okay. 4,500 meters is the average depth of the abyssal plains. And I just want to make something clear. 4,500 meters is the average depth of the abyssal plains. The average depth of like the whole ocean is something like 3,800 meters. So why is it different? Why is the depth of the whole ocean average less than the depth of the abyssal plains?
The abyssal plains is the deepest point, so we're taking an average of the deepest points of the ocean.
Yeah, you're taking the average, but remember that the average of the whole ocean would also include the continental shelves, which are very shallow. Okay, so that's why there's a difference there. But these, on average, are 4,500 meters deep. They're very, very flat, and they're very, very deep. Okay, so why are these parts so flat? It's because this is like the last stop of all sediment on Earth, right? So you can imagine all the sediment on Earth, it's all kind of flowing to the lowest point. And the lowest point, well, besides the trenches, which are fairly few and far between, the lowest point are these abyssal plains. So all the sediment ends up there, and it just kind of covers up all of the surface features. So it ends up being very flat because it's all covered with sediment. And sediment, we're going to get into all the sediment next week. But sediment goes anywhere from like, there are actually some places in the ocean, actually here in the Gulf of Mexico, where the sediment's like 10 kilometers deep. I kid you not. It's like 10 kilometers deep. There are other places where there's maybe just a few meters, right? But anyway, yeah, sediment. We're going to get all into everything about sediments pretty soon. Probably 1 kilometer of sediment is maybe average for the ocean, but it varies wildly. Like I said, it could be anywhere 10 kilometers to a few meters or a meter. So you got all that. So we talked about fracture zones, and another thing we might have to talk about are one thing I did want to also mention are things like some of these hotspot islands, things like that. So besides volcanic arc islands that form at, so where do volcanic arc islands form at? Where do they actually form at? What kind of zones do they form? Yeah, subduction zones, right? So besides that, there's also random kind of volcanic islands that form. So a good example of these is Hawaii. And so Hawaii is not a subduction zone. It's just a hot spot. And what's kind of cool about the way this works is that there is a kind of thermal anomaly that rises from the core mantle boundary. There's a mantle plume. It's a thermal anomaly. And it just happens to be a hotter part of the mantle, and there's a lot of melting going on here. And it creates these islands. But what's kind of cool is that as the Pacific plate moves over this hot spot, it creates a chain of islands. And so the current, right now, Hawaii, the big island, is over the hot spot, and it's active. As you go to Maui and Molokai, Oahu, and et cetera, the islands, you'll notice, do you see how the islands get smaller and smaller and smaller? So why are they getting smaller and smaller and smaller? Yeah, so I'll explain a little bit what happened. So when those islands first formed, they were as big as Hawaii. But why are they smaller now? What could have made the islands smaller?
The water rising?
Water. Well, yeah, water definitely has something to do with it. And the water, it's think of all the waves and
Erosion.
the rain and erosion and wind, and over time those islands have eroded away because once they move off the hot spot, they're not being built up anymore by volcanism. And so they're kind of like dead islands, and they start to erode away. And actually what will happen is they'll erode away so much that they go underwater. And so they'll be underwater islands. We call those underwater islands seamounts.
So seamounts are like underwater islands. They're islands that used to be islands, but they've eroded now below the surface. So this will give you a pretty good idea about how this forms. So notice how they start to erode now after they've cooled down. Okay, so that's why you get these subsequently smaller and smaller and smaller volcanoes. And I want to show you something. This is actually really crazy. So yeah, this is showing how it becomes a volcanic island that gradually sinks below the surface. And it's kind of interesting because what will happen is coral reefs will develop on the outside. You ever see Moana? And the reef, and you don't go beyond the reef, right? So the reef, the coral reef forms around the island like that. It's just a natural buildup of coral. And what's actually kind of cool, you'll see this happen all the time, is that the island will actually dissolve away. But the reef, remember the reef is alive, and the reef is constantly growing and maintaining itself. So the island will be gone, and you'll just get a circle of reef, and there'll be nothing there anymore except for the reef, right? And those are called atolls. So you can actually, if you look at, like, if you go on Google Earth and you like look around the South Pacific, and you can actually find all these different atolls there. So it happens a lot. And one thing I wanted to show you that's pretty crazy too. This is, maybe I should have made this bigger. Okay, here's Hawaii down here, okay? And you can actually do age dating of all of the islands. So the oldest island is maybe about 10 million years old, right? And of course Hawaii, the big island of Hawaii, is currently being built, right? So it's 0 years old, okay? And maybe the oldest one is like 10 millions. But there's actually seamounts. This is a crazy thing. Look at this. There's seamounts that go all the way 65 million years old, that go all the way and connect. Do you see what this chain of islands is right here? That's another volcanic arc island. Those are the Aleutian Islands off the coast of Alaska. So this is a crazy thing. Hawaii has this chain connecting it all the way from Alaska to the current islands of Hawaii. There's a whole chain of seamounts of old islands that go from Alaska to Hawaii. Isn't that weird? You think because you think Alaska is totally on the other side of the, other extreme, right? But it really is. It's really true. So that's been happening for 65 million years. Okay. So anyway, so there you go. Those are how atolls form and how volcanic islands form. The one kind of last
feature that I want you to just have heard of here are things called plateaus or oceanic basins or plateaus. So oceanic plateaus, not basins, oceanic plateaus. So one very prominent one is the Ontong Java. It's off the coast of Java. So it's the Ontong Java Plateau. So there you can see it right there. So these were just tremendous outpourings of basalt that happen once in a while. And they're just tremendous, tremendous outpourings. So this is about 120 million years ago. And there was a 30-kilometer thick outpouring of basalt that happened. Imagine that, 30 kilometers. Oh, sorry, there's actually should be a thing there, 30 cubic kilometers. But they created these huge plateaus here. So these are very shallow parts of the ocean that are just kind of boisted up by these tremendous outpouring of basalt that happen. So there's a few of those scattered throughout the oceans as well. So those are all the different features of the ocean basins you've learned about. And I think I've answered everything, right? So we're all done with ocean basins. We'll go on to sediments next time. And I don't think I have any announcements. Oh, I guess leave your, what is it, number 8 now? Do you want to leave number 8? Lecture assignment number 8? And I will see you next time. Have a good weekend.